WA 16 number 5. An electric motor turns a flywheel through a drive belt that joins a pulley on the motor and a pulley that is rigidly attached to the flywheel as shown in the figure below. The flywheel is a solid disc with the mass of 64.5 kilograms and a radius big R is equal to 0.625 meters. It turns on a frictionless axle. Its pulley has much smaller mass and a radius of 0.230 meters. The tension, TU, in the upper taut segment of the belt is 138 newtons, and the flywheel has a clockwise angular acceleration of 1.67 radians per second squared. Find the tension in the lower slack segment of the belt. Alright, so here's our diagram, and these are all the known constants that the problem gave us. The mass of the big flywheel is 64.5 kilograms. The big radius is 0.625 meters. The smaller radius in here is 0.230 meters. And the tension in the upper rope is 138 newtons. And the acceleration of the flywheel is negative 1.67 seconds to negative 2. And the problem tells us that the angular velocity is in this direction, and so is the angular acceleration, denoted by this negative sign right here. So you may be confused as to why this force down here is acting in this direction, even though the object is spinning in this direction. Well, just like up here, for example, you have the rope is pulling in this direction, so this is the direction the force is acting. Down here, in a similar manner, the rope is in this direction, so the rope is pulling in that direction, meaning that the force is going to have to be in that direction. So starting off with our basic formula for torque, net torque is equal to I alpha. And this torque on the top here, which I will denote as TU for the torque on the upper portion of the wheel, is acting in the negative direction because it is causing a clockwise rotation. So negative TU plus TD, because this is causing a counterclockwise rotation, is equal to negative I alpha. And the I alpha is negative because it's acting in a clockwise direction, which is what we denote as negative. So the torque on the upper part can be written as the force on the upper part times the radius, a similar manner with the torque on the lower part. And we know that the moment of inertia for a disk is 1/2 mr squared. Notice here that I'm using big R because it's the whole object that is rotating, not just a little part in there. Now I'm going to do some algebra here and solve for FD because this is what the problem is asking us to solve. So first I'm going to add this term to the other side. I'm going to divide through by the small radius. And now I'm just kind of plugging all of our known constants. The big mass is 64.5 kilograms. The big radius is 0.625 meters. The angular acceleration is 1.67 seconds to the negative second power. And notice here that I plugged in the magnitude of the angular acceleration because this negative sign here already denotes the negative direction. The tension in the upper rope is 138 newtons. And the radius of the smaller wheel here is 0.230 meters. Again, the smaller radius is just 0.230 meters. Plugging this all into your calculator and rounding to 3 significant digits, because that is the amount of digits each one of the constants given to you has, yields 46.5 newtons. When I first attempted this problem, the error I made was assuming that this force, and therefore the torque, was acting in this direction. So then I did all the work the same, and I got a negative answer. And the negative answer, I understood, meant that my direction was flipped. so I had to flip around the direction of the force to get an accurate understanding of the system. This problem shows that I'm able to manipulate the torque equation, net torque is equal to I alpha, and I'm able to understand and quantify systems with more than one torque. Thank you.